So today we talk about deep learning testing, and the first remark is that we'll mention some scientific results during my talk. They are mostly results obtained by the pre-crime ERC project and by the pre-crime team. So all the credits go to the members, the fabulous members of the pre-crime team. So why deep neural networks and why testing deep neural networks? Well, they are an emerging technology. They are embedded in many software systems nowadays because they have been very successful in solving problems that in computer science have been there for a long time. They have been attacked by different approaches, but it's only with deep neural networks that we have obtained a technology that gives very good performance. When we are talking about processing images, for instance, recognizing objects in images, or processing videos, processing audio, for instance, performing speech recognition tasks, processing text, natural language text, and also some tasks related with code have been quite successfully dealt with by deep neural networks. The output of these deep neural network is typically a class or a numeric value, depending on whether we are solving a classification or a regression problem. So for instance, an example of a class can be the type of an object or an entity appearing in an image. An example of a numeric value for a regression problem can be the prediction of the steering angle or the throttle of a self-driving car. But neural networks can do more than that. They can have in the output also another image, a video, an audio, a text, or some code. They can even generate code. On the right, you see remarkable examples of applications and usages of neural networks. Here you can see Google Translate. I guess everybody knows it, and it embeds some Google neural machine translation technology that is used to produce nice and smooth translations like this one. Here you see an example of a self-driving car where the prediction is the steering angle in the Udacity simulator in this example. And here you can see a quite noticeable recent application of neural networks to the code, where the output is code, the input is text that describes the functionality that we want, and Copilot produces the implementation of that functionality. So it's a success story. It's increasingly used. It's increasingly used in safety-critical applications, in business-critical applications, in health-critical applications. That's why testing is very important. But if we start to look inside these components, we immediately discover that they are quite different from the code, traditional code we are used to. So in code, you have some complex computation logics that determines how to produce the output. If you look at the code that implements a neural network, you will find something that is typically very boring. It's just a flat list of instructions that just create a network and train it, because actually the behavior of these components is determined by the training process, not much by the logics in the code. The logic basically does not exist. The code is there just to set up and run the training process, which is the one that determines the behavior. And looking inside the training process, what's really important is what training data we're using, what architecture we're using for the neural network, and how we set the hyperparameters. Another remarkable difference is the kind of contract that we stipulate with a deep learning component. If we have traditional code, the contract that we stipulate is a precondition implies a postcondition. This is a contract for a function that computes the square root of a number. If the number is greater than or equal to 0, then the output multiplied by itself will give the input. So it's a logical kind of contract. If you look at the contracts that you stipulate with a deep learning component, these are probabilistic contracts that promise some degree of accuracy, which means if a set of test data is provided as an input, then the prediction accuracy will be 95%, which means still 5% will be mispredicted, which means that we have to deal with these mispredictions somehow that are declared in the contract. So here we can hope that a perfect implementation, we all know that no perfect implementation exists, could achieve the contract. Here, the contract itself is not promising more than 95% accuracy, and that's an important difference. So the explosion of deep learning techniques has led the software engineering, the software testing community to migrate many of the traditional software testing approaches to deep learning. And here you see a list of some examples with examples of instances. So input generation, automated input generation is one example. And as you can see, the specific techniques that are used to generate test inputs for deep learning components are pretty specific, pretty peculiar. We talk about adversarial example generation, input perturbation, or generation using generative adversarial networks, which are other neural networks that generate test inputs for the network under test. So the techniques are pretty different because of the nature, as we have seen in this slide, the nature of deep learning components is very different from the traditional software. And the same holds for the other testing techniques and approaches that have been migrated. So there's recently an explosion in the software testing literature where the traditional approaches are migrated. So for instance, how to prioritize test inputs in the deep learning domain can be based on the uncertainty of the neural network under test, which is something we don't have in traditional software. Adequacy criteria don't work at all, the traditional ones in testing deep learning components. Branch coverage, if you look at this example, branch coverage doesn't make any sense. There's no branch, there's just a flat sequence of instructions that is trivially covered by a single execution. So researchers propose a new criteria like neuron coverage, surprise adequacy, that are, again, specific and peculiar to the deep learning domain. So that's good. I think a lot of very interesting research has been published recently in deep learning testing. We made a lot of progress, I think, and it's really an exploding field. On the other hand, some important questions that should be asked because they require a different answer and a different elaboration in deep learning testing remain sort of implicit. So for them, either the same answer that we got in traditional software testing was used, which not always works, or it was just it was just ignored and it was taken for granted. So here's some examples of very fundamental question. What is a bug? So apparently you don't need to answer this question. We all know what is a bug, but as we will see, that's not so obvious in deep learning testing. And the answer, depending on the answer, you can have misconceptions and you can have consequences on the experimental results that you get. What is a valid test input? Again, validity of test inputs is something that we don't care much about in traditional software. Maybe there's a precondition that checks it. We will see that this is very important for deep learning testing. Determinism of deep learning systems, that's an important property. Of course, we have non-deterministic software also in traditional software testing, but we will see that non-determinism that we have here is quite peculiar. When is a fault detected? That's also sort of trivial. Traditionally, we will see it's not. Similarly, when is a mutant killed? And what is a unique failure? We observe a failure. Is it a unique or have we already seen it? We will see it's not a trivial question. So I guess these are the questions that will guide my keynote in the next remaining time of the keynote. And I will try to answer them and I will try to explain why I think some misconceptions can arise depending on the answer that you give to them. So let's start with the most fundamental one. What is a bug? So we can consider traditional software. We can look at the IEEE standard glossary, and it's described as an incorrect step process or data definition in a computer program, which means a mistake a developer makes when writing the code. Great, but we already noticed that with a deep learning component, the code is just there to set up the training process. So the probability of making mistakes there is low. Of course, we can make them, but the incorrect bit can be probably elsewhere. Even if we don't touch the code, we might have different behaviors and better or worse behaviors depending on the other aspects that affect the training process. I already mentioned data, the hyperparameters, and the neural architecture. So whenever we observe like a crash or self-driving car, and we want to know what is the bug behind the crash, looking at the code is typically not enough. So in order to understand more deeply what is a bug in a deep learning component, one of the first work that we did in deep crime was to develop a taxonomy of real faults. So the methodology that we used is based on repository mining and interviews with developers. The sources of information are Stack Overflow and GitHub for repository mining, plus 20 researchers and practitioners that we interviewed. Then, based on a systematic labeling procedure, we developed a taxonomy of real faults, and which was then validated with 21 more researchers and practitioners. And if you look at the taxonomy, some parts of it might look more or less familiar. If we say there can be a bug in the API usage, that's something we are used to, but there are some bugs, some sources of bugs or faults that are very specific of deep neural networks. For instance, bugs that affect the architecture, the model. There can be missing layers or redundant or wrong layers in a given architecture. The properties of a layer might be wrong, which means that if we use them, we get a poor performance, but we improve them, we improve substantially the prediction accuracy. Activation functions in the layers can be a source of bugs if they are wrongly set, and model type and properties can also be set wrong. The training process is an important source of faults, of bugs, of mistakes. In particular, hyperparameters are pretty critical, and setting them wrong can lead to poor performance. Choice of the loss function that is minimized in the training process is very important, and also choice of the validation and the test set. The quality of the training data, if we have unbalanced training data with wrong labels, or in general low quality, here you can see all the subclasses of the poor quality in the training data, that affects potentially negatively the behavior of the neural network to really a major extent. Pre-processing, the training process itself, the choice of the optimizer, these are other sources of faults. So faults that affect a deep learning component are very peculiar, which means that if we want to mutate a neural network to simulate what we have when it's faulty, we cannot use traditional mutation operators. That's why we developed deep crime, which inject artificial faults that affect either the training set or the network architecture or the network hyperparameters, producing a so-called mutant, a variation of the neural network, which is a mutant where a good test suite is able to show that the accuracy drops. So if we produce a mutant, then we can use it, first of all, to evaluate whether the test set is good or not. And we deem a test set good if it can discriminate an artificially faulty model from the original one, which means that it can show that the accuracy of the faulty model is substantially lower than the original accuracy. In that case, we, through mutation analysis, similar to what we do with traditional software, but now with specific ad hoc mutation operators, we can assess the quality, the adequacy of a test suite. We can also use mutation analysis and our tool, DeepCrime, can be used for other purposes. For instance, to compare input generators to see if they can expose the artificial faults associated with the mutants. We can use them to benchmark repair tools or to assess test prioritization. These are just a short list of possible uses. They are quite in line with the traditional uses. And if you want to look deeper into DeepCrime, you will see that the mutation operators that we implemented in it are matching mostly one-to-one with the fault categories that I just showed you in our taxonomy. So we have the training, the faults affecting the training data in the taxonomy with some subcategories of faults, and each of them is mapped, is implemented as a mutation operator in DeepCrime. Good, so we know now more or less what is a fault or a bug in a deep neural network. We have a better understanding, I hope. Then if we look at the existing research and approaches, we can identify some misconceptions. So first one is that a misprediction is not necessarily a bug. So as we have seen, a bug is something that can affect any component, any element of the training process. But when we use a deep learning component as a component of a bigger system, the contract that we make with that component is a probabilistic one. So we have some probability of a correct prediction and some other probability of a prediction error. So if our tool, if our new tool is exposing a prediction error that was already there, because it's part of the 5% of inputs that is too weird to be handled properly, then we have not discovered any bug. In a way, in traditional software, if we break the contract, we satisfy the precondition and break the postcondition, we have found a bug. Here it's slightly different because there's no warranty in the contract that there will be no misprediction. Second, when we are doing repair, then, as we have seen, the source of a fault is in the training process. So fixing, adjusting some weight is not the same as repairing the root cause of the bug. It's more like patching the system. And reporting the number of discovered bugs can be very misleading. Because, as I said, prediction errors are there already in the original test set or even in the training set. There are some inputs that are mispredicted. If our tool is just discovering those inputs multiple times, then we cannot say we have discovered multiple bugs because we have discovered actually nothing really new. Second question is about validity of the input. What is the valid test input? This again might look like a weird question, but it's because of a difference between traditional software and neural networks. These three beautiful images are taken from the paper by Dola, Dwyer, and Sofa, so credits to them. And they compare what we do in traditional software if we have basically preconditions. If the input is valid, we do something, otherwise we have a precondition violation. A neural network is different. We provide an input and get an output. Here you see an example. You have a neural network that can recognize automatically a digit, a handwritten digit. So if we provide a letter A to the input, we get as an output 4. This is digit 4 for the neural network. So it doesn't make any sense. This is not a 4, but there's no validity check. Any input produces an output. If we provide an input, an image with some shades, we get a 5. Doesn't make any sense. If the input is something between a 1 and a 7, so it's impossible or it's impossible to label with confidence for humans, we might get a 7. If we provide an 8, but with some little dots here that implement an adversarial attack, we might get a 3. But again, it's very unlikely that a handwritten digit will have these dots placed, with these white dots placed exactly here to confuse the neural network. So inputs can be invalid because they belong to another domain. They're just not completely out of the distribution of the inputs because it's impossible to label them, or because they cannot appear in nature, in reality. But neural networks don't check for validity. So the authors of this work propose that we should introduce an out-of-distribution detector, and only if the out-of-distribution detector is satisfied, we proceed with the computation of the neural network. That makes a lot of sense. Of course, it matches the preconditions that we have in traditional software. The problem is that validity of the input is a very weird and complicated notion for deep neural networks. What is a valid input? So my answer is that it's an input for which a human can assign a label with confidence, so with no ambiguity, and an input that can appear in nature, in the real world where the system is supposed to operate. That's my answer. And from the answer, you can immediately see that it's very difficult to operationalize it, to automate, as we do in traditional software with a precondition, the check of validity of an input. So the same paper that I just cited by Doran, Dwyer, and Soffa proposed also in an automated way, to approximate the validity check. So doing it precisely is very difficult, probably impossible, but one way to approximate it is, as proposed in this paper, by using autoencoders. Autoencoders are neural networks that compress the input into a latent space and then decompress it, and they come with a reconstruction error. If you compare the reconstructed input to the actual input, you get an error. And this error is bigger if we provide the input something anomalous, so we can set a threshold theta to decide if the input is in the distribution of the training set or out of the distribution. And that's one way to approximate validity. Another similar way proposed by the self-oracle is still using autoencoders, but now the threshold for a comparison is obtained only from the training data by finding a fitting of a gamma distribution and excluding some predefined false positive rate. This was presented at ICST in 2020. But these approaches are limited to an approximation of what can be actually measured. There's an input generator that we developed that can explore the frontier of behavior, so it can find pairs of inputs that are very close to each other, but that satisfy the property that on one of them we have the correct prediction, 5, and on the other we have a misprediction. This is called a frontier input pair. And then when we did this work, we considered the problem of the validity, because when you generate inputs, if the input is invalid, is outside the validity domain, then it's not really useful for testing. We don't care about how the system behaves on invalid inputs. So what we found in this study was that the validity of the frontier depends on the quality of the network under test. If the network is low quality, then the frontier is hit with a lot of valid inputs. If it is high quality, we have a lot of invalid inputs in the frontier. But to be able to decide if something is valid or invalid, we had to involve humans. So in the end, all the results that we presented on the validity of the generated inputs are based on human assessment of validity, because assessing validity is intrinsically a very difficult problem. So I hope I convinced you that assessing validity is important, but it is also difficult. What are the misconceptions that we can have if we just ignore this problem? Well, first of all, that we cannot say that small perturbations are producing really test inputs that fool a neural network, because they might not be realistic. They might be perturbations that are never met in reality. They can only be there if an attacker deliberately injects those perturbations into the input. So they can be useful for security testing, simulating an attacker's activity, but not necessarily for testing. Validity assessment is difficult, but it's pretty important. And if we just overlook or ignore it, we might again report results like my tool generated 1,000 failure-inducing inputs win. Well, not necessarily, because all of them or many of them can be really invalid inputs that don't make any sense, that will never appear in any realistic usage of the neural network in the field. So validity affects results that we report in terms of failure-inducing inputs to a major extent. Determinism, that's another important factor. So if we train a neural network, we take it, we provide an input, we get an output. If we provide the same input again, we get exactly the same output. So a trained neural network is completely deterministic, 100%. Yeah, there are some special cases, I'm not mentioning them, but let's say standard ones are completely deterministic. However, the training process itself is highly non-deterministic. The initial weights are assigned non-deterministically. Optimizers often make non-deterministic choices, plus usage of the GPU can introduce non-determinism. So if you have a neural network architecture, you train it 5 times, you give it 5 times the same input, sometimes you can get one output, it's an 8, sometimes it's a 9, which means that the question whether this input that we have generated maybe automatically has exposed a fault or not, a misprediction or not, depends, I mean, on the training process. We cannot say we train once, we find a misprediction, okay, we found a fault. No, because maybe if we train another time, we might get a different prediction. And actually, we have to give up to a sort of Boolean notion of failure of fault detection, and we have to accept a probabilistic one. So this input exposes a misprediction of this neural network with a probability of 60%, because 3 times out of 5 it gives a misprediction, twice it doesn't. So fault detection becomes a probabilistic notion, which means also that coverage is also probabilistic. We cannot say we covered this number of levels of activations of the neurons, because if we train another time, we can get different coverage measure, mutation scores. All the traditional metrics that we use in testing now become probabilistic, and these we recognize and reported this at ICST in 2020 in a paper where we investigated mutation operators, and what we found is that if we take, so as I mentioned before, a mutant is killed in deep learning testing if the accuracy on the mutant drops. Good. So if we train once the mutant and once the original program, we might or we may not observe any drop in accuracy. So what we have to do is we have to train multiple times the original piece, the original program, and we will see that even the original has some variation of accuracy. So accuracy is not a single value. It is here between 70 and 80% across different retrainings of the same model. And then we have to do the same with the mutant. We get a different distribution, and then we have to compare statistically this distribution. If they differ significantly with a small p-value and no negligible effect size, we say the mutant is killed. So here, again, we can have a lot of misconceptions that actually I have seen in many papers as a reviewer. So fault detection, coverage, mutation score, they cannot be assessed on a single instance, because if you train twice or 10 times, you might get different results. You cannot say I fixed the seed once for all, and then I don't need to do multiple trainings, because this does not eliminate the non-determinism of the training process. And performance or quality metrics on single instances might not generalize if we train multiple times. Great. Failures, that's another metric that is often reported. So we are testing a self-driving car, and we crash it 6 times. Here you can see 6 images of the crashes that we have produced. Great, we have obtained 6 failures while state-of-the-art produced only 2 failures for this training car. But is it really 6? Because if you look at this crash, it looks very similar to this one, and this one, and this looks very similar to this one and this one. So maybe these are not really 6 failures, they are 2. They might differ slightly by some orientation angle of the car hitting the border of the street. Fine. Still, I don't think we can consider these as really 6 different failures, because actually they are not useful to developers as 6 failures. Each of them points to one specific, so in total to 2 specific conditions in which we have a problem. Similarly, at the bottom, we have 5 fives that expose a failure, but they look all very, very similar. So the underlying problem is probably the same. So to summarize, when we talk about failures, diversity matters. And this is very important if we do test input prioritization. Here you can see that here we have 6 inputs that can be prioritized in this way or in this way. If we prioritize inputs in this way, then here we expose one misprediction because it's predicted as a 6 while it's a 5, then no misprediction, and then we get one more and one more. Here we have all the 3 mispredictions one after the other. So traditionally we measure the area under this curve, which is 50% higher, and we say this ordering is better than this one. But is it really better? Because at the end of the day, this failure is exactly the same, repeat just 3 times. So if we just ignore that, if we just ignore the uniqueness of failures, then we might get orderings that look different, but in reality, from the point of view of exposing failures for developers, they are the same. And actually, if uniqueness of failures, so if the possibility of exposing the same failure multiple times is ignored, then APFD is also not really very useful. What we should do is just measure top K accuracy, because we are just classifying the inputs as misbehaving or non-misbehaving, and we want to put all the misbehaving ones at the beginning according to any permutation. So uniqueness of failures is extremely important when we are doing input prioritization. We did some work on a characterization of the uniqueness of failures. In particular, we defined feature maps that can be used to organize the failures and to interpret the failures. Just to give you one example, in the case of a self-driving car, 2 possible features are the mean lateral position, that's a behavioral feature of a car, and the minimum radius of the curve of the road that we are driving. Here you can see all the behaviors organized by these features, and here you can see the misbehaviors, and each of them differs, each one in each cell differs from the others by some feature that we are measuring. So we don't measure the misbehaviors or the failures, we measure the feature map cells filled with misbehaviors. That is a more meaningful measure of unique failures discovered by a given technique. So again, if we ignore uniqueness of failures and diversity, the importance of diversity of failures, then first we might miscount failures. And second, we might end up with an input prioritization process that actually is no more an ordering, a ranking process. It's just a classification problem between mispredictions and correct predictions, where the ordering doesn't really matter, while if we introduce diversity, the order does matter, and prioritization becomes again very meaningful and important. Good, so I tried to answer a number of questions around the deep learning components, and they look trivial sometimes or fundamental if you want questions, but I hope I have convinced you that the answer to these questions is definitely not trivial or obvious, and it can, point or bring to misconceptions that we want to avoid. So I would like to end my keynote with a positive message, which is a set of guidelines for the deep tester. And the first one is being careful when discovering or even repairing bugs, because we care about bugs only if these are bugs that are not covered by, are not already part of the contract, are really new conditions that were unknown before that produce a misprediction. Validity of the inputs that we are using or generating is very important. If we are producing failures or discovering faults for something that can never happen in reality, then we are not discovering anything. So validity should be incorporated when exposing faults. The very notion, some very basic notions and metrics like fault detection, coverage, mutation score become statistical ones. You have to be aware of that and keep this in mind when doing experiments on deep learning testing. And exposing a lot of failures can be very easy if they just differ by imperceptible little bits. So diversity of the exposed failures is really important.